So two mechanisms in this, they're extremely closely related. This is not the same as alkene makes hydrogen sulfate and then gets hydrolyzed to make an alcohol. This is the direct hydration rather than the indirect one that goes via hydrogen sulfate. When an alkene and water are put together under the right conditions, which is to say in the presence of a concentrated strong acid catalyst, we only ever use H2SO4 or H3PO4, then the forward reaction as I'm showing it here, making an alcohol, is hydration. You put in a water molecule in across the double bond. Under those same conditions though, an alcohol can be dehydrated, which is to say have a water molecule's worth of atoms taken out of it. Sorry, dehydration is what I meant to put there. And there we are. They're so closely related that we really should look at these two mechanisms together because the intermediates are the same actually. This mechanism, or these mechanisms, were put onto the spec in 2015 in like the newest sort of version of it. We hadn't seen them before, and the few questions we've had on them where you've had to draw the mechanism have mostly been incomplete mechanisms where they've started you off and then they say finish it, or draw some arrows which are missing and such like that. So we'll start with we're going to do propene again. Now, because there's an element of asymmetry in propene, butene would have been a better option, but this will do. I'm only going to give you one of the possible outcomes, and I'll always go for any secondary options that I can, you'll see. But again, the question will clearly direct you if there's a choice to be made about which product you're supposed to get when there is a choice. So it all kicks off with H plus from the acid catalyst interacting and combining basically with the alkene. So this is from our concentrated sulfuric or our concentrated phosphoric acid catalyst. Water will appear, but it's not here in the very first step. So the alkene is effectively like activated to make a more reactive species by bonding with this H plus from the acid catalyst. That gives us an intermediate. Now let's just take the template that we've started with. The double bond becomes a single bond, and here again there is a choice which carbon does it go on. I'm going to use a bit of colour coding for this one. Plonk the H plus from the acid catalyst on the left hand carbon. It would happen to both, there'd be a major minor split here, but that's not for now. As we saw in electrophilic addition, this carbon is kind of left empty handed. Whenever you see a carbon with 3 bonds, it almost certainly should have a positive charge on it if you've correctly got 3 bonds on it. There we are. Now at this point, water makes its appearance. Let's use a green pen for the H2O molecule. Water has obviously got 2 lone pairs on its O. We need to show one of them really. Water's not a great nucleophile, but it will strongly attract. It will react with C+ like this. It wouldn't have done that, with like a haloalkane or something where there's a C delta plus, but it will here. So the next arrow comes from the lone pair on the oxygen atom of a water molecule to the C+. That doesn't give us an OH alcohol though. We've got an OH2 group being put on here. Now I'm going to have to go around in a little loop on my mechanism. Again, admire the colour coding. So in purple pen, here's the atoms which were brought to the party by propene. In pink pen, we've got the H plus that came from the acid catalyst. It's not H plus anymore, it's just a hydrogen atom bonded. And we've now got this OH2 group attached as well. Now, just like whenever you see a C with 3 bonds in a mechanism, it almost certainly should have a plus on it. Just like whenever you see an N with 4 bonds, it should have a plus on it. Whenever you see an O with three bonds, it should have a plus on it. In organic chemistry, not in transition metal complexes. So we don't yet have our final product. We're almost there though. So now if I just finish this off, think of it like this. We say that the acid that gave that H plus at the beginning is a catalyst. We know that catalysts don't get used up overall, and so there must be in this final step like a replacement of H plus so that there's no net loss of H plus from start to finish, and that's exactly what happens. So if I draw the final product, and then we can maybe, or you can decide, or maybe you already know what should happen next. So there's the propene's contribution. The original H plus from the catalyst is permanently locked away in that structure now. It's not coming off. So it's not the same H plus that's about to be relieved. We know that we're headed for an alcohol here, something like that. So it must be one of the OH bonds that breaks then. Either of them, they're equally good, can be shown to break. And obviously whenever you break any bond in a mechanism, the arrow comes from that bond to another atom. Now where does it go? It can't go to the H, because that would make a hydride ion, a H minus, like a H with 2 electrons in its outer shell. Not what we're looking for, we're looking for H plus. So it must go to the O plus. And the O is positively charged, maybe there's some sense in that. So actually, by the end of it all, there is a H plus that's been put out to replace it. It's not the same one. The H plus from the acid catalyst is put into the structure and is then replaced by a H off the water molecule that also gets inserted as the alcohol group. Now, take a closer look at these intermediates then. We started with the alkene, we went through a carbocation, so that's a lot like electrophilic addition. Then we went through this hydronium intermediate, this OH2 plus group attached, and then we finally got to the alcohol. So alkene, C plus, OH2 plus, alcohol. When we look at dehydration, we go through these same 4 species, those same 2 intermediates, but in reverse. So we'll start with an alcohol and an acid catalyst, we'll go to that, then we'll go to a C plus, and then we'll end up with our alkene. The arrows are going to have to be different, but that's that. If you wanted to practice this, then I suggest you just do it again with butyene, and get butanol, and then check the patches. In the same video then, let's roll on to look at dehydration. So that clearly is hydration, that's the direct hydration, because we're adding water to something, literally adding it into the structure. So dehydration then. I'll pick a different alcohol and I will use butanol actually. So butanol, here it is, and I'll just expand the structure out slightly. Now, as we'll see by the end of this, again, there are actually 2 different alkene products possible here. A bit like when we were eliminating a haloalkane, if you had like 2-bromobutane, you can make but1ene or but2ene depending on which side you form the double bond on, and that's the same. That's true here as well. I'm going to make but2ene, but just be aware that we could make this look different. Now, here we go. So it's acid catalyzed. So there's the H plus from conch sulfuric or conch phosphoric acid. It's an alcohol. It has a lone pair, actually has 2, but there's a lone pair on the OH group there on the O, and it is the atom that's going to form a bond. So strong acids such as conch sulfuric and conch phosphoric acid, strong acids are incredibly good at forcing H plus onto things. And again, alcohols, just like water, they're not brilliant nucleophiles. They have got lone pairs, but they're not particularly willing to share them or leave them. However, when you've got a strong acid, a concentrated strong acid at that, firing off H pluses, so to speak, this OH has no choice really but to accept it. It's just how it goes. So even though it wouldn't normally, in the company of a strong and also a concentrated strong acid, the OH acts as a nucleophile and forms a bond with it. Now, again, just a quick flashback. The intermediates: alcohol, OH2 plus, C plus, alkene, and that's the order that I've just gone in that we're going to go through now, which is the total reverse of the direct hydration mechanism. Whoops, wrong page. So, first of 2 intermediates, we've got an OH2 plus group, where the OH was before. So we've protonated the alcohol functional group. Whenever you see an O with 3 bonds, stick a plus on it. I'm keeping that CH2 expanded for now, it's a bit unnecessary. There we are. Now again, that's not our final product, and we know that we're headed for an alkene here because we're doing dehydration, and alcohols dehydrate down to alkenes. So what do you think has to happen next then? Well, the next intermediate that I know we're expecting to see is a carbocation. I've remembered that, and also it would make sense that now we've got this OH2 plus group, that would be happier. Nature would be better off if that was dropped off as a water molecule. So that's exactly what happens. This OH2 plus group departs the structure, so this CO bond has to break. So there's an arrow going from the CO bond, and it's going to go to the O plus, and that then liberates the H2O molecule. So the OH gets turned into a water molecule. That's a good leaving group. It leaves the structure. The arrows always go to the positive ion if there's a charge, like an N plus or an O plus. So this is our second intermediate, it's the carbocation. That's got a positive charge now. The CH2 and the CH3 either side of it are unaffected until now. Now, as I said, there are two possible outcomes here, because what has to happen next is the C plus has to doubly bond to one of its neighbours. And again, because this molecule that we started with is asymmetrical, you know, bonding to the one on the left does not give the same structure as bonding to the one on the right. So there's a split here. It's not to do with major minor because there's only one carbocation, it's a secondary one, that's irrelevant. But it's more to do with something else that we don't actually have to talk about called Markovnikov's rule, which you may have heard of but you won't find in your A-Level revision guide, so don't worry about it now. But basically, either side can do this. It's preferable, nature prefers it, if like the double bond carbons have more carbon attached to them. But that's going outside of the spec and now is definitely not the time for it. So I'll show one of the carbons in the middle. So if the C plus is carbon 2, I'm going to pick carbon 3, the other one that's not at the end of the chain, and I'm going to have one of its hydrogens falling off. Now remember, H plus was a catalyst in all of this, so the H plus has to be regenerated by the end. So there's a CH bond on a carbon of the carbon which is next to the C plus breaking off, so there's bond breaks, and it goes to the C plus or to the CC bond, either way. That gives us our product, which is now butene. So all of that is still intact. The H that I drew the arrow coming from, or rather the CH bond where the arrow is coming from, that H is now broken off. Both electrons in that bond went away from the H, so that H doesn't have any electrons, H plus, and that's because this arrow represents this bonding pair here becoming this bonding pair here. So we've now got our double bond. So there's butene. Just because I said it and I don't want to cause confusion, alternatively, it could be that rather than a H on the CH2 to its right, the way I've drawn it, it could be one of the three H's in the CH3 to the C plus's left. So if I just expand that out a bit, I'm going to have to expand the CH3 on the end to do this same step, basically. So there's the C plus. I'm just focusing on that CH3 now instead. So I'll actually condense down the CH2 that we've just worked on. It's the same structure, just represented differently. Alternatively, this can happen, where any one of those three H's from the left side breaks off, forming a H+. In which case you get butanene, because at that point you can hopefully see that the double bond is at the end of the chain. And there we are. And again, we mentioned this in another video if you've been watching them, that if this was the outcome, then you can get butanene, butene, and then within butene you've got E and Z isomers there as well actually, so there's quite a lot going on. There we are, hope that helps.